Hello, and thank you for joining us tonight for the USGS Public Lecture. My name is Mitch, and I will be your host and moderator today. I have some quick announcements to make before I introduce our speaker. Next month, on August 25th at 6 p.m. Pacific Time, we will have USGS geologist Dave Solar talk about the National Geologic Map database, a world of information at your fingertips. If you are watching this on a desktop computer and need to turn on closed captioning, please look at the bottom right-hand corner of the screen for the closed captioning icon. It's the one with the two little C's. You can also use stream text for captioning. Please see the stream text link provided in the Q&A window. To access the Q&A panel, you can click on the question mark icon in the upper right-hand corner of the screen. At the end of the lecture, we will have a Q&A session, and this is a panel where you can submit your questions to our speaker. To submit your question, click on the question mark icon located on the upper right-hand corner of the screen. And now it's time to introduce you to our speaker. Joining us tonight is Dr. Prasad Pankabals. He is a supervisory research geographer with the USGS. He is a world-renowned expert in remote sensing science with multiple major contributions in the field for over 36 years. He has worked in over 25 countries. He's been recommended to the Department of Interior to become a senior scientist and has been placed in the list of the world's top 1% of scientists. He obtained his PhD from Ohio State University in 1992 and has 168 publications, including 2 seminal book sets, the Remote Sensing Handbook and Hyperspectral Remote Sensing of Vegetation. Prasad has conducted pioneering research in hyperspectral remote sensing of vegetation and of global croplands and their water use for food security. Dr. Thenkabail is at the center of rendering scientific service to the world's remote sensing community. This includes serving as editor-in-chief from 2011 to now of Remote Sensing Open Access Journal and the associate editor since 2017 of Photogrammetric Engineering and Remote Sensing. The USGS and NASA selected him to be on the Landsat science team. Without further ado, I'm going to pass it over to Prasad.
Thank you very much, Mitch, and Christy for all your wonderful organization of this talk. Much appreciated. Now let me start my presentation. Okay. Good evening, everyone, and welcome to everyone from around the world. I know many of you are joining from different parts of the world, and so it could be different time zones, and I really appreciate you joining this talk. What I'm going to talk today is mapping the world from satellites, helping us understand global food and water security in the 21st century. As you all know, that we have just still struggling with COVID, even after 2 years, and already there is a talk about monkeypox. And then we have this situation in Ukraine, which is causing turmoil to almost entire world in terms of, we see this in everyday news in terms of inflation and especially food inflation, which is a basic human need and for peace and harmony and livelihoods of people around the world. So how do we get an objective data of food security, water security for the entire world? That will be my topic today. I would like to start by acknowledging some of the contributors to this talk, my colleagues, Dr. Parthasarathi Talaguntla, Dr. Adam Oliphant, Itia Anisi, and Daniel Foley, who are part of my team. What I will do today is create this talk into 3 big parts. The first part is give you a background on croplands, population, water, and climate. How did we manage in the past in terms of food and water security? How are we going to manage in the future? And how are we going to manage in terms of when given the changing climate? So I'll give some background information that will be valuable. Then my second part of the talk is about the paradigm shift in how we do, how we look at this data. I call it paradigm shift because a collection of data, technologies, and tools have come together. For example, there are hundreds of satellites and even thousands of satellites that are orbiting our planet today that send out data to us. And that is really, I would say, mother of all big data, really. So you handle big data, and then there are technologies to handle that in terms of machine learning, cloud computing, artificial intelligence. How do you put all these technologies and tools together to solve problems of the world's using these powerful data sets of the world's problems, such as food and water security, and to provide information on that. And finally, part of the talk will be to provide some concrete information on at least one of the products and how we do this. Let me give you a background. When we talk about global croplands is tied up to all these components. Land is very much essential for food security, availability of water, because croplands consume nearly 80 to 90% of all human water use, even up to 90% of human water use in most parts of the world. Even global average is about 80% of the human water use consumption. This is both the green water and the blue water. And then leveraging this and of course, food security needs also have been met by leveraging land and water. Some people may have more land, more water, and other people might have other resources, but not so much land and water. So you can trade that either country-wise or regional-wise. How do we do this in a changing by adapting to climate change? Not only croplands are required for feeding humans, but also for animals and our nutritional need. And if you look around the world, many economies are actually, I will show even most developed economies are actually, I will call them agriculture-based economies. And it's so important for peace, harmony, and sustainability of people. Of course, energy is central to all this. Let me begin with the slide on world population. This is a history of the world in terms of population for last 12,000 years. 12,000 years, there was a population of about 4,000 people. No, sorry, 4 million people. And there is a 2,000 times increase in population today, about 8 billion people. And if you see, Mexico and Brazil were top countries in the very beginning of that. About 7,000 years back, China and India take lead in population. And this remains true to even to today. There were parts of the history of the world's population when India and China's population was more than the population of the rest of the world. And so you can see how countries, keep changing here. And primarily what you see is as we enter CE, the common era, sometimes the India's population was more than the entire world at sometimes. And China's population kept on varying, so it'll go front, go higher, come lower for various reasons. So you can see that. And when the last millennium, you can see here about, so again, China around 1,300, 400, about 1,700, China will start becoming the #1 country in the world. Now it will suddenly go into #1 country in the world. India, basically, this is a colonial area for India. The population, there was stress in population. And now you can see United States now comes in last 175 years and Russia, Japan, and other countries. So what is interesting is population is so important. for everything else that we do on this planet and how we do things in the planet. So if you look at, for example, 3000 BC, there was 36 million people. Even 1 AD, there was just 145 million hectares of croplands. And from next to 1900 years, nearly 2000 years, the agriculture cropland area, according to population, it also grew up to nearly 850 million hectares. But look at this, from 1900 to 2000, the croplands doubled. And just in 100 years, that shows the stress on the planet in terms of the resource needs to meet the demands of this population. And over last 20 years, our recent work shows it's about 1.8 billion hectares of croplands. So when we have these kind of activities, of course, there is this climate issue. 2019, about 36,000 metric tons of carbon was emitted from the entire world annual emission. That came down to 34,000. That is one good thing during the COVID era 2020 by 2,000 metric ton. But that again will go up for sure. So about 40,000 metric tons of carbon is released into atmosphere every year. And major emitters, of course, China, US, India, Russia and Japan, and you can see the 10 leading countries of emissions. In that, of course, the three main emitters are industries, transport and energy. Agriculture plays around 18% of the emissions, but that is not just 18% because there is, of course, this transportation where you spend a lot of fuel and emissions into atmosphere. And a lot of other agribusiness industries also that comes into picture. So agriculture it plays a key role in both carbon emissions and sometimes carbon sequestration as well. So ultimately in Paris summit of COP21 2015, world came into an agreement that from a peak of 45,000 metric ton of carbon, we want to go to zero. This net zero thing that people are talking about, that's around 20, let's say between 2060, 2070, at least by 2100, we should reach that depending upon various scenarios. How do we do that? That doesn't mean we are not going to emit. Either whatever is being emitted is being absorbed in terms of in oceans or forests or soils, or we are going green in terms of solar or wind or going through electric cars and so on and so forth. So what you so far saw was there is a big connection between population growth and then population growth and the stresses on the planet and subsequent carbon emissions. And how is that all related to food and water security? So let us look at this. How did we manage so far in the past food security, especially from end of the Second World War to present, about 75 years, world population grew from 2.5 billion to nearly 8 billion now. About 5.5 billion people came into the planet. How did that happen? Yeah, we use this terminology called green revolution. What is green revolution? Green revolution is combination of things. That is, for example, increase in yield as we went from 1960 to, you can see here, continuous increase in yield per unit area of production. How did that happen? Genetics, inputs into agriculture, better crop management. Then intensifying cropland. That means if you have a piece of land, you grow not one crop, but on the same piece of cropland, you grow a second crop. And increase in area, both irrigated and rain-fed areas kept on increase as we go from here, from 1900, you can see here. And then irrigation, because irrigation, of course, produces more food than rain-fed, purely dependent on rain. And also there is much more stability in how you produce your food. Green revolution doesn't mean is limited to this. There are many other factors that you will see, but in a basket that the world dealt with meeting the food demand and nutritional demand of the populations till today through this measure. Irrigation areas itself, you can see here the distribution of all the green areas are distribution of irrigated areas. Irrigated areas produce about 2 to 4 times greater yield than rain-fed areas. And till 1900, irrigated areas were almost negligible. By 1950, end of Second World War, about 1945, about 50 million hectares. Then after the Second World War, World Bank, IMF, and other and also countries, they funded a lot of effort into irrigation projects, built major reservoirs in the world that contributed to greater food production. For example, India and China, for example, together have about 60% of world's irrigated areas. And the beauty here is because of the climate, in these areas, you can not only grow one crop, but you can grow a second crop and sometimes even a third crop in a year. The other way that people manage food in the past was what we call as virtual land and virtual water. That means you may not have land to grow food, but you imported food like last 25 years in China, because of their economic growth and etc. So we say China imported about 10 million to 25 million hectares of cropland from other countries. So it is not your land, but you are using other people's land for you. But US, for example, 10 to 25 million hectares of cropland they exported. This is virtual. This is not real, but it's virtual. By growing corn and soybean and exporting it to other countries, and similarly maybe sugarcane and exporting it to other countries. Similarly, virtual water. That means since agriculture takes up nearly 80 to 90% of all water use, you can see here, for example, Europe, 100 to 305 billion meter cube. That is 100 followed by 12 zeros. 100 trillion liters of water being imported, or even more, because it is a range here. And in fact, if you look at the data, we can blow it up and see which country use how much. But you got an idea, so there is a tremendous amount of water imported because you are importing food grown in other countries. And then other people are exporting water like US and Brazil. So this is also contributed to food stability. See, we are living in an interconnected world, so we cannot avoid all these pandemics also showing us that how interdependent we are from each other, and a problem in somewhere in the world is a problem for everybody else. That kind of a scenario. Now, how are we going to feed in the 21st century? Now, 2050 world population from UN projections going to be around 9.5 billion, and by end of the century it will be 11 billion, given the current population projection. So there are 3 possibilities for increasing food production, and they are closing the yield gap. I'll tell you more about it. That is, you are producing more per unit of land, are increasing crop water productivity, that you are producing more per unit of water, and adapting to climate change. How do we do that? Through climate smart agriculture, extreme weather agriculture, drought tolerant agriculture, but maybe some genetic engineering or whatever, you make plants grow even in extreme conditions, and so on and so forth. So you increase per yield per unit area, you increase the production per unit of water, and you also adapt to climate change and produce more. There are many other, you will see there are many other solutions, but thing is, these are the main 3. So if you look at cereals alone, the yield gap is, that means, for example, if you look at Midwest US and Canada, they are producing optimal crop production. But all these red areas, you can see there is actually shortfall. There is a possibility in this cropland to grow more food. So how do we do that? And it's possible in the same land by either nutrient application or through irrigation, just to give 2 examples. But again, is that what we want to do is another question. That is, for example, do we want to build more reservoirs of water reservoirs and really kill the river systems? You know, that's a big ecological debate going on. So especially the lessons learned from what we have done in the past. Similarly, we are polluting all our groundwater by high application of nutrients like nitrogen. Do we want to do that? But if you do more nutrient application, more irrigation, of course, you can produce more even in the other, that is the yield gap areas, and produce more. That is basically for the irrigation itself. You take in world, there is about 1.8 billion hectares. This is about 12.6% of the terrestrial area. 35% is irrigated, 65% is rain-fed roughly, and all the rain-fed is in yellow and irrigated is in green. So if you produce, for example, this 35% of irrigated area produces nearly 50% of the world food production. The 65% of rain-fed area produces other 50%. That shows basically if you have irrigate more areas, you can grow more food with less land. And so that's a possibility that one could consider. So Snyder et al., they did a research and came up with a paper recently, and I was reading this, and they say they propose that you can reduce actually cropland from 1.8 billion hectares at present by 37 to 48%, almost even making it half of that, and still grow same food. But that depends upon inputs, that depends upon irrigation and many other genetics and many other factors. But is that what we want to do? So it's not as easy as what we think is possible. This is a theory, correct? The theory into practice is a big difference. So, for example, Africa is a continent where the present population is about 1.3 billion people, and it will go to 4 billion people in this century. Only continent where there is a tremendous increase in population. But how are they going to meet food demand? And Africa has only 15% of the world's population, but just about 6% of the world's irrigation. So definitely, if you increase irrigation, the production can go up, but that is just, is put that on the table. There are two ways of in the future to expand food production. One is by cropland expansion. Look at the history, that the slide, the population slide that I showed. 4 million people in 12,000 years back, and 8 billion people, 2,000-fold increase, always happened with cropland expansion. But during 2010, something very interesting happened. Intensification of cropland exceeded cropland expansion for the first time in the history in this one. That means that, for example, if you look at Brazil, for example, over last 25 years or so, expansion increased and also intensification, that means growing more than one crop, also went high. Whereas in Southeast Asia, China, etc., expansion was stable, that is stable, and intensification was actually high. That is, intensification was high. And US and Canada, both were expansion was stable because expansion has already taken place over last few decades. And intensification also has been moderate because one problem of intensification in northern hemisphere is the climate. You can't grow really next 2 crops and 3 crops. So all these factors come into picture. But you remember I put those 3: increasing crop production per unit area, increasing crop production for unit of water, and climate smart agriculture and all that. But also you can put all these possibilities into combinations. For example, can we do more of urban and peri-urban agriculture? Let us stop from cities growing into, for example, I live in city of Phoenix. Lot of agriculture area here is taken up for building cities. Should we stop that and keep that into agriculture? Hydroponics, for example, hydroponics is a place where you grow crops without soil. So I'm not going to read all this, but you can see here there are basket of things that are available for increasing food production going forward. But the challenge is climate, of course. So if you look at, just to focus on US, the climate models project US getting hotter. By 2090 to 2100, it will be very hot. That means, for example, if you take Midwestern US, with getting so much hotter, will there be enough cropland? Because you can't grow same amount of food if it gets hotter. There will be yield reductions. You will need more cropland. Is there enough land? So that question. Second is, if the temperatures go up, of course you need more water to grow the same amount of food. Is there enough water? So is there enough land? Is there enough water? This question comes. So you have to factor in climate into this basket of things that we are looking at. So we have many questions, many possibilities, and many strategies. So currently we have 1.8 billion hectares of cropland. So we can say, can we grow enough food with the existing cropland? Can we grow enough food with the existing allocation of water? Like the paper I showed, can we grow more food with reduced cropland and reduced water? Actually, this could be the way forward, really. We have to find a solution for this. But how do we do that? With ecologically friendly way, environmentally friendly way, and by meeting the climate demand. And of course, there are various other exigencies we have to take into factor. We have to take into factor like pandemics. We have to take into factor wars and disasters, and see that what all of this says is croplands are in a state of flux. They are not, going to remain what they are today. Somewhere it is going to increase, somewhere it is going to come down. So here comes what I call as a paradigm shift in basically satellite remote sensing. Here comes satellite remote sensing. And I am talking here about 21st century satellite remote sensing. I remember the days when I did the PhD, in 1992 from the Ohio State. It was a different world altogether. We worked with one satellite image to do my PhD. And my interesting story is each time I went to my professor and asked for an additional image, he said, you will never get done, Prasad. But now look at this. The entire planet is covered with satellites, hundreds and even thousands. We have a lot of microsatellites. These are CubeSats and others launched by private enterprises. Sometimes they launch 50, 100 satellites at one go. Of course, we have a history of satellites. US had its first Earth observing satellite in 1972 called Landsat. We are celebrating 50 years of Landsat. What a wonderful time it is. And the Landsat itself is such a fascinating satellite that has served the planet so well. But we have other satellites now, various other satellites that are orbiting. Just I'm talking here about the Earth observation satellites. There are, of course, other type of satellites, GPS satellite, climate satellites, geosynchronous. Most of these are sun synchronous satellites. So the other thing that has come into this paradigm shift is having this humongous amount of data, but the ability to handle that data. One is we are now, because of the cloud, we are able to create analysis ready data. By analysis ready data, to give you a small example, is convert all the data into some kind of a normalized, harmonized format and stack them all into hundreds or even thousands of layers of data. And then use machine learning, both for example, supervised and unsupervised approaches of, for example, random forest, support vector machine. These are, supervised machine learning algorithms. And for example, K-means is isoclass. They are unsupervised classifications. I don't go into technical details of this, but we have basket of machine learning algorithms, and also hierarchical segmentation. It's an object-oriented classification. You can actually use this satellite data and process them initially, code and compute them all in cloud. And you can do that at a planet scale. And this data is acquired almost now sometimes on a daily basis and at a very high resolution. And then once you gather this data and then process it, understand the information content, you finally get into automation and artificial intelligence. That means once you are able to produce certain products, then you can start automating. that process. That computer itself can start understanding what you are doing and then probably can give you products that are valuable. Let us look at what are those type of products. Here I want to say something very interesting. So if you look at this now, for example, this is a global mosaic of a 3-meter data set, and you can see here time-lapse image. So if I click on that, any parts of the world, you can see how it is. It could be a daily or weekly composite or a monthly composite or whatever. This comes from satellites that are like PlanetScope DOWS, which is 3 to 4 meter data, the spatial resolution. And then there are rapid eye. I'm not going very technical here. SkySat, Landsat has been there for a long time, 30-meter resolution. When you talk about 30-meter resolution, 30 by 30 meter, it is 0.09 hectare. Think about that. Sentinel is a European satellite. The beauty is that you can actually combine all these satellites and use the data in ways that are valuable. So what I want to show is that data is acquired along the electromagnetic spectrum. Here we are going from 350 nanometer to 2500 nanometer. For example, this is a visible spectrum. This is a red-dot spectrum. This is a near infrared spectrum. This is shortwave infrared spectrum. You can have few bands or many bands. That means you can have bands in every few nanometers, or you can have a band, for example, let us say from 500 to 550 nanometer, or you can have 500 to 505, 505 to 510. So you can have either few bands or hundreds of bands, and each one of them acquiring data. And there is a beauty of this acquiring data in various electromagnetic spectrum. For example, if you acquire data in a 970 nanometer, you are actually basically looking at this, you can know about the quantity of water being absorbed in the plant. That is why you can already say there is a high water content in the plant, this absorption. This reflection shows higher biomass. For example, this is visible spectrum, basically looking at pigments, carotenoid, anthocyanin, and all those plant chemicals. When you have this high reflectivity, you know it is kind of a drying plant. That, for example, with high absorption, we know healthy plant. This kind of a thing. But the idea here is that the data is acquired across the various electromagnetic spectrum, and we can use that data to produce various cropland products for food and water security. So let us see what type of products. For example, we can use this satellite data for the entire planet, acquired from different data, composed in cloud and computed on the cloud. For products like Cropland Extent, where are the croplands? Where are croplands of the world? Where are irrigated areas versus rain-fed area? What type of crops grown? Where are they grown? What is the intensity of crop? You can click on a pixel here and basically know what is the whether they are growing one crop there, two crop there, using the time series data. That is not all. Those are the 4 products that I showed there, but then you can go any number of products that are required to solve problems. Like, for example, crop tour stages, cropland fallows. Why do we need cropland fallows? For example, if you leave, say, 10% of the land as fallows or 20% as fallows, that means you are using less water, correct? For example, if you make a decision in a particular region which is water scarce, we say, OK, let us grow 10% less crop this year to save water. And then you are able to save a humongous quantity of water by just that simple decision. But once we have this product, we can do crop productivity, crop water productivity, and biophysical, biochemical quantities. What happens is you have a satellite image. This is how you are seeing in the field. This is how you are seeing in the satellite. And this is the information content. All the red areas are showing very high productivity. These blue areas are showing low productivity. And in a small farm, why there is so much variability? How can we reduce this variability to produce more food per unit of land within this particular farm? Those kind of decisions can be made for anywhere in the planet. So mapping the world's cropland using the Earth observing data. So let me give one concrete example today so that for you get an idea about how satellites are used to map croplands of the world. So for example, I'm defining cropland as, the standing crop, cropland fallows, and permanent crops. All of them put together are croplands. So we divide the entire world into agroecological zones. There are 74 zones, and these are based on climate, for example, temperature, long-term temperature, long-term precipitation, and soils, all climate and agricultural factors, and divide them into zones so that it becomes much more easier to understand and map the croplands more perfectly. And I was earlier showing how in the electromagnetic spectrum you gather data for the different bands, blue band, green band, we call it, depending upon where they are in the electromagnetic spectrum. You gather that data, and also transformation of this data into, for example, normalized different vegetation index or whatever, and then time composite them. Not to get too technical here in this lecture, but you can get them into areas and finally compose them for an end of a stack of data set for an entire year, so that we can look at what is happening in the world for the entire year. And there are situations where there are cloud issues, and those can be usually sieved out by using data from the previous image and next image, what we call as peak counting. This is very technical again. I'll skip that. So we have each zone in the world. You have data cubes, and those data cubes are processed on the cloud by coding. And like, for example, you write Python script for machine learning and say, this is this class, this is this class, if all that. And how do we do that? And we do that by knowledge base. Of course, in computers, it's always garbage in, garbage out. So we need to have a precise knowledge. For that one, we gather what they call as reference data. This is a reference training, training, testing, and validation data. We can split them into training, testing, and this is to train the machine learning algorithm, test them, and to validate them. So for example, you gather from each of these samples, these kind of, either based on precise ground geographic locations, or from very high resolution data. You can gather data and say it is cropland, non-cropland, and then put them all into some kind of a cloud. And because satellite images also in the cloud, based on these data points, then you can plot them continuously. For example, all these plots are, you see here how many, there are thousands of plots. They are basically plotting over a month of January to December. How is the vegetation index changing? If you are seeing a lot of these at the very lows, that means it is kind of a barren land, fallow land, desert land, that kind of a thing. Lot of vegetation dynamics happens here. And something is growing, it is going up, something is coming down. So then there is a whole process of interpreting all this. So this is how you collect this data to say this is cropland, this is non-cropland, and so on. So this is the knowledge base that is required for the machine learning. For example, this is cropland, the one in red, and the one in blue is non-cropland. You can see there, these are for season 1, season 2, blue band, green band. So in different bands also, you can see here, for example, in the red band, there is maximum separability. Even in season 2, you can see maximum separability. And when you see this one, you still see some samples, virtually, giving some confusion. That's what we ultimately say, errors of omissions and commissions. That cannot be avoided, but that can be avoided by bringing in some other data. Let us say, bring in thermal data, bring in elevation data, slope data, and so on and so forth. So you use machine learning algorithm, you use random forest, support vector machine, HSEG, all sorts of different machine learning algorithm using all these samples. And then we get this fantastic map. This is a lot of work. It's not as simple as you see, but you can see here ultimately for all the 74 zones that I was showing, and we say where are the croplands, where are non-croplands. I will finally at the end of the lecture show a bit of how to navigate this one. in high resolution. So when you go high resolution, you can actually see every data point and then see very much details of these. For example, in US, you can zoom in and even look at a centrifuge farm. So this is such a high detailed data, really. So how do we know it is all good? So we do an accuracy assessment. For example, if you are in North Africa, we do what we call as an error matrix. How well is cropland mapped as cropland? We say it is 92%. That means 8% of the cropland we did not map, and the 8% are omitted. And when we say user accuracy, it means commission. That means non-cropland coming into cropland. That is about 11%. So we can do these accuracies for entire world, and then you do an accuracy map of the world actually. So this is showing basically overall accuracy. You can also do for producer user accuracies. Most of it is 85% and higher, which is very good. Then, of course, once you produce these products, you can calculate areas. For example, for every country in the world, you can calculate how much cropland is there. The total cropland in the world is 1.873 billion hectares, correct? So out of that, there is, for example, India has about 180 million hectares of cropland. US has about 165. I will show because this scaling is not very good here. But thing is, you can see here all these different countries showing different cropland areas. So for example, China 165 million hectares, India 179, US 167, Russia 155 million hectares. The 4 leading countries in the world in cropland areas, net cropland areas. So net cropland area is different from grass cropland area, which means in the same area you can grow more crop in a given year. That becomes grass. So anyway, net cropland area. And what is very important here is look at some of the countries compared to geographic area. Moldova, San Marino, Hungary, they nearly have more than 80% of their land geographic area under cropland. Ukraine, for example, 75% of the country is under cropland. So yeah, now you can see the importance of, for example, Ukraine, Russia, Belarus, and all those conflict areas in terms of food production. I'm talking about here, and also much of the European countries. You look at, we think Europe as kind of industrial countries. I always call them Europe and Asia, South Asia as the agriculture capitals of the world. UK, for example, 64%, France 58% of the geographic area under cropland, Italy 61%. Ukraine itself, Ukraine and Russia together contribute about 25% of the world's wheat, 20% of world's corn, 50% of the world's sunflower oil. So Ukraine alone contributes 40% for the World Food Program, wheat. So you can see the implication of this on food banks of the world. Based on the situation that's there at present. But what is also very important going forward in the years to come is that Russia, Ukraine, and Belarus produce natural gas nitrogen, which is so crucial for all the anhydrous ammonia, urea, and that is nitrate, ammonia nitrate, etc., used in as a fertilizer in agriculture. And they are the major exporters for the world. So if you don't send that, for example, do you remember the Sri Lanka situation? One of the reasons the country production went down was they basically banned the import of these products. This one. So I want to show, these 3 countries which are highly agriculture. This is how it looks like. And I want to play a small video here for your benefit. And this is a video. When we traveled in France, we took it on a train, and you can see here, this is in France. The agriculture, I put this because to get you a feel of how agriculture is in, for example, in France, like much of Europe, they are not just London, Paris, and those kind of things that are what most people think they are, but that is much beyond that. And if you look at per person, per capita agriculture, you see Uruguay, for example, 2 to 3 hectares per person. India and China just 0.1 to 0.25 per person. The smallholder agriculture is a big issue. You have a lot of land for agriculture, but per person it's very less because of the population. There is also irrigated and rain-fed cropland. So in the world, which is so important, the distribution of that, you can see that it is same methodology that what I am showing is you can produce any number of products like this of different types for to meet food and water security. Irrigation roughly 35%, rain-fed 65%, and how much they produce and where are they distributed. You can see here California, for example, fully in this one, and US itself. US has about 23% irrigated and 77% rain-fed cropland, and their distribution is, irrigated is in green, rain-fed areas is in yellow. Crop dominance product. You can see here, this is a single, any point in the world, you can see how what crops are grown and when they are grown based on the signature. Ganges Basin, 2 crops. This is South Africa, for example. This long growth season shows this is sugarcane. This is wheat and corn, grown in these months and all that. So you can do crop dominance or crop type products for the entire world. So also, this is one of my final slides, is to show the crop water use. For example, as I said, irrigation uses 90% of human water use. Look at India, for example, using 685 kilometer cube per year water. That means 685 followed by 12 zeros, trillion liters of water that is being used. So tremendous amount of water is being used for agriculture. One way of by allocating water for other uses is to reduce this one or make it more efficient. So what is the impact of our work? Nearly from 2018 to 2021, nearly 126 countries downloaded our data, and how they downloaded. This is just a map to show a simple impact figure. There are many publications that you can see, and we have you can visit this website. You can download our data from here. You are also download our data from NASA. This is the NASA sites. Basically, LPDAC is the storehouse for downloading our data. You can also go in to croplands.org and visualize yourself at full resolution. And there are, of course, many publications, but much of my talks today also covered in the USGS professional paper. And I have some concluding thoughts, and the concluding thoughts are that, croplands, if you look at the human history, for 4 million people in 12,000 years back to today, always cropland expansion. Now there are many other things that have come in. There is no enough land for growing, expanding. So we need to find other solution, and we also make it sustainable and environmentally friendly. There are a lot of uncertainties, but ultimately we have to make it sustainable, environmentally friendly, and we have an opportunity to use big data, machine learning, cloud computing to really process all this data and provide this information on a very frequent basis. I will at least say very reasonably every week also possible. And I've shown the various different type of products that are available. I want to finally, before I end, want to show, for example, this is a cropland product at croplands.org that you could go in, visualize, and so when you go into this kind of thing, you can see at a high resolution, you can basically look at anything. For example, if I go here, let us say, see this product, you can look at it here, and then if I take the opacity out, you can see the details now. You can see every farm there. So that's being mapped. So and this one, all you have to do is, where are these cropland, and just one more thing. And for example, you can go to northern Nigeria, for example, and you can zoom in, and you can look in what is there, So Yeah, you can see here all cropland, and these are trees. Actually, these are farmlands. And if I put it, it's all covered except this area. Anyway, that's the end of my talk. Just to give, and I'm happy to take any questions.
I remember you talk about getting data back in the day. I remember doing a remote sensing class where I loaded a single Landsat scene on the computer and would say, okay, let me go get a cup of coffee. I can have about 45 minutes to talk to somebody before it would even load on the computer.
Yeah.
So things have progressed immensely since that time. Still, actually, we don't have any questions from the public. I have one though. I was noticing you were talking about where you can grow crops and whether economically feasible versus ecologically feasible. So I was wondering for areas that are like drought stricken, like California Central Valley, which is, hugely economically, it's a food basket. It may not be ecologically sound to grow crops there, but we still do.
Well, the thing is, we know that California was a dust bowl turned into, a green bowl, basically based on irrigation, correct? Nearly 85% of California. California has about 12,000 acres of cropland, the Central Valley. And out of 12,000, every year, if you look at it, around 12 million acres of cropland. Of that, about 10 million acres of cropland is they produce something every year, and this can be wheat, corn, soybeans, and a lot of nuts. It supplies nearly 25% of U.S. nuts. Yeah, but in the sense, how do we we need to balance. See, what is important is the soil itself is fertile. Even the same can be applied to Arizona to grow crops. If you get water, the soil is fertile enough to they're rich in organic matter, so you can grow crops there. But then you have to balance between balance between what you can grow in to meet the demands of the people, and at the same time, how do we preserve sufficiently for environment, and this is for flora, fauna, and requirement of let us say for fish, animals, feed. So we need to balance that out and plan that better.
Right. So it's kind of important you plan what you grow and how you irrigate what you've got.
Yeah, exactly. And also some of the, for example, let us take rice versus wheat. Rice, for example, for producing a kg of grain, it takes almost twice the quantity of water compared to wheat. So if you want to save water, can we increase wheat versus rice? That is a good solution to save water, but at the same time produce more food. But then are the people who are really eating rice ready to eat wheat, that kind of a thing. So that kind of balancing is always there.
Right. Okay. And we've got a couple questions here. First question is, growing food vertically indoors, a good resource for the long run?
Yeah, exactly. So in the sense, as I said, in the basket of things that I put in, hydroponics, for example, this is becoming very popular. We are growing crops without soil. Greenhouses have been in existence for long, and especially for urban areas where you don't want to transport, for example, let us say a vegetable from 1,000 miles away. You want to grow that locally. Then you need to create an environment wherein you have enough greenhouses and even vertical or horizontal, depending upon the land availability. You can grow this in the local environment, so you not only sustain your food needs, at least much of it or some of it locally, so that, for example, in situations like pandemics, you are not so stressed that your shipment did not come from country X, which is located somewhere. So that's a good, it's one of the basket of things that we need to find solution to find a solution.
Right. Another question from Anonymous. Great presentation. What do you think will be the best strategy going forward to grow croplands from your personal experience?
Yeah, that's an excellent question, because see, now people are telling, okay, now we can, one thing is clear, there is no more expansion of cropland in the world. You can, unless you want to cut down forests and destroy, or it is pretty much unproductive land where you want to grow. So expansion is ruled out. Intensification is that means in the existing cropland. In many countries, cropland intensification has only about, let us say, 10, 20, 30% of the croplands have been used for intensification. That is a great opportunity there to intensify, maybe use short season crops. In fact, we have written some papers on this as a second crop, wherein they consume less water, but also give more income for farmers, and you are able to produce more food for the people as well. The other thing is about crop water productivity. That means you have to find ways of producing. See, for example, rice crop, a lot of areas, rice is grown in a very inefficient manner. You are leaving flood irrigation, gravity irrigation. The gravity irrigation basically wastes much of the water that you are leaving it to the field. Probably if you supply, my famous what you call saying always is, you actually release 10-20% less water to fields, and probably nobody notices it, and they actually produce optimal yield anyway. Because it is a human nature. You apply more water, you produce more, which is not true. You need to have optimal water use. Crop water requirement is what we need to meet, and so there is a tremendous potential. By increasing crop water productivity, you can save a lot of water and produce more. So in both crop water productivity, increasing crop water productivity, and increasing intensity, you are already producing more food in the existing land.
Okay, question from Mark. Are the irrigated croplands 100% irrigated? For example, can you split the portion of water from rain and irrigation on the irrigated croplands?
Yeah, very good question. See, we have in cropland two philosophy, that is the green water and blue water. The green water is purely rain fed. That means rain falls, crop grows, and you harvest. And blue water is basically you are supplying water through artificial means and you are growing crop. So, but there is a fusion between the two. You get some water from rain, but that is not sufficient enough, and then you supplement it where maybe there is one irrigation you provide. Maybe this year it rains more, so you don't have to give a second irrigation. There is another year where there is a drought situation, you may have to provide a second irrigation. So it brings more stability to what you are doing in terms of agriculture. But yes, you need, when you define irrigation, see, the other thing I have to say is, when all this mapping, whether cropland is okay, but when we map, for example, irrigation versus rain fed, definition is the key. For example, if you supply one water during the growing season, do you call that irrigation or not? Yeah, or do you call irrigation only if you supply water all the time? Maybe there are 5 waterings during the growing season. So how you define it? So, but I think the solution is to balance between what you get from rain and what you need from to really optimally grow crops by supplementing irrigation when needed.
Okay. Another question. Is there any effort to influence type of crops grown? For example, vineyards are great, but they don't feed the world.
Okay, that's again an excellent question. See, this is a thing that this is when it comes to policy. For example, what you grow in a particular region, I can say as a scientist what can be done best to optimize everything. From resource wise, from meeting food demand, meeting nutritional demand. But policy wise, I cannot say. But thing is, what can be done is, say, if you are in a region X or country X, you have certain amount of people, and you know how much grains you need and how much, for example, other type of food like fruits, vegetables, nuts, etc. you need. And then you can say, okay, now, and also there is economic need for farmers. So you can say, okay, now earlier I gave this wheat versus rice. Similarly for cotton, for example, cotton crop is, is a cash crop. Sugarcane is a high water consuming crop. So do you want to really grow more sugar? Sugar is also not so healthy, and do you want to grow so much sugar that consumes a lot of water? Do you want to grow a lot of cotton, which is a long water consuming crop? Do you want to balance that with the crops that are much more less water consuming and maybe can grow in shorter period and can meet the food demand? So it's a complex chain of events that has to take into consideration of farmers' needs, in terms of economic needs of farmers, what is required for the people in terms of both food and nutrition, and the cost of food and all those factors. Okay, that's but there are solutions to that.
Okay, couple more questions here. Can you comment on the impact of transporting the food to the intended consumer?
Yeah, these supply chain issues, especially during this COVID period, we have realized the food prices. One of the reasons the food prices are going up is we have had supply chain issues. So that's where for example, vegetables. Most cities and towns can grow their own vegetables. It's not a policy prescription, I'm going to say, but I'm as a scientifically saying that, okay, you can have a sufficient amount of greenhouses. You don't have to export cauliflower from traveling 1 month on a ship from somewhere. Probably you can grow that. Every place can grow it in a water effective area. So again, it's a policy issue. What can be done locally? Maybe sometimes it is cheaper to produce it from somewhere and get it than you do it. But then in pandemic you are in a fix, correct? Or not pandemic only, but in terms of wars and turmoils in the world, some kind of crisis of other nature. So you will have. So again, you need to balance that out in terms of what is best for your people.
Okay, last question. Can the layers be downloaded for GIS application?
Absolutely.
I did put the links for the Global Foods Security Support System and the Global Cropland data in the Q&A.
Yeah. Our data is all published in NASA LPDAC. So anybody can, these are with the, data sets along with the algorithms and etc., documentation, etc. In fact, that's what I said in terms of impact. We have around 126 countries. Even in 2021, we had nearly 96 countries download our data. So anybody can download from anywhere. And this is free service, and those links are there in my presentation. If somebody didn't get it, you can always send me an email. I can point them to you. So anything that we do is in public domain and anybody can download this data and use them.
Okay. Thank you again, Prasad, for joining us tonight and answering questions from our audience. Also, thanks to all of you for joining us tonight. This lecture will be available for on-demand viewing in about a week on our website at www.usgs.gov/PLS. You may also see tons of previous recordings on our website under the multimedia section for videos. We've been doing these lectures for about 20 years. If you would like to subscribe to be part of our monthly mailing list, feel free to send us an email at wmcesic@usgs.gov, and we will happily add you to the list. So please join us again next month on Thursday, August 25th at 6 p.m. Pacific time, where Dave Solar will talk about the National Geologic Map Database, a world of information at your fingertips. We will see you next time. Good night.
Thank you, Mitch and Christy. Bye. Thank you, everyone who joined.